Hello, everybody. Thank you for joining. Today, I will discuss testing noisy linear functions for sparsity. This is based on joint work with an Indian Dove from UPenn and Rocco Sabodio from Columbia. Let us warm up by reviewing some classical results in learning linear functions and sparse recovery. Consider the following problem. Let W denote a hidden linear relation that we want to recover. Say we receive a bunch of random equations about W with plus or minus 1 coefficient. Like the first equation is W1 minus W2 minus W3, blah, blah, is 7. The question is how many equations do we need to recover W? In this talk, we reformulate it as a learning problem. If we write down the plus 1 and minus 1 coefficients in every equation as a vector x, the number on the right-hand side of that equation is just the dot product between the hidden vector w and the coefficient vector x. In other words, each equation is a sample of the form x w dot x, where x is a random plus minus 1 vector. So for convenience, in this talk, we call w dot x the label of x. So the learning problem is how many samples in this form we need to learn w. From the classical Gaussian elimination, we know n linear independent equations are enough to reconstruct w. So that's all I want to say about the learning general linear functions. Next, let us discuss sparse linear functions. In many natural settings, the unknown vector w is sparse or approximately sparse. For convenience, let k denote its sparsity. This is saying w has at most k non-zero entries. The natural question is how to improve the learning algorithm given the sparsity k. The seminal results in compressed sensing by Donahoe, Candace, Robert, and Tao give efficient algorithms to recover W within theta k log n samples. So the running time is still polynomial in n, and the theta here means that we have information theoretical lower bounds. So this is what we know for solving sparse linear functions. Next, let me tell you our consideration. Basically, we consider the decision version of this sparse recovery, that is, how to decide whether W is k-sparse or not. So let me define the problem in the next slide. So my algorithm still receives a bunch of samples of the form x w dot x. The goal here is just to distinguish between the following two cases. In the first case, the vector w is exactly k-sparse. In the second case, w is far away from k-sparse. There are several ways to define the distance between w and k-sparse vectors. In this talk, we just say for any k-sparse vector v, the relative distance between v and w is at least epsilon, that is epsilon times the L2 norm of w itself. Okay. But our algorithm, you will see later, will be very robust that can handle all the definitions of distance. Okay. So another thing I want to say is that for convenience, let us assume the sparsity k is a constant like 5 or 10. The error epsilon is a small constant like 5%, and the L2 norm of w is a constant, say between 1 and 2 in this talk. So a few clarifications. In our problem, we always assume the hidden vector w is in these two cases. And the output is just the first case or the second case. So I want to address that our goal is not to learn w, but to distinguish between these two cases. The second thing I want to add is our motivation, because the decision problem is not harder than the recovery problem. So the main motivating question of this study is, can we solve the decision problem more efficiently than the recovery problem, say using fewer number of samples? Just try to give the first taste of our result. We answer yes for this question in a certain sense. In particular, as a special case, when we draw x from plus minus 1 to the n, our algorithm will take k over epsilon to the order of k samples to decide whether W is k sparse or far away from k sparse. Now I want to give a short comparison of our results with the recovery bound, that is theta k log n. So the dependency on the sparsity k is worse in our bound, but the dependency on the ambient dimension n vanishes in our bound. Actually, the main feature of our bound is the independency with n. And I want to say that we are not really recovering the vector W. Even for sparsity 1, it needs log n samples. Okay. Another thing I want to add here is that we will consider x generating from order distributions, say an n-dimensional distribution D, like uniform on the solid Boolean cube, that is the interval minus 1 to 1 to the n. And the noisy samples, say we add the Gaussian noise eta on the label w dot x. So in this setting for recovery, the seminal work of Candice, Robin, and Tao shows how to recover W with k log n samples in 10 polynomial in n. So before I formally state our results, let me review some previous work. So our work is inspired by the algorithmic considerator from property testing. Let me recap the standard model of property testing. The given query access of a Boolean function f. The goal is to decide whether f has a fixed property p or far away from that property. There is a long line of research on property testing. Some notable example is Honta testing, which is an analog of sparsity for Boolean functions. Firstly, let me point out some differences between our problem and the standard model. So we only get random samples rather than query access on the function f. At the same time, our functions are real valued and promised to be linear plus noise. But a key conceptual similarity is that a large body of work in property testing tries to achieve sample complexity independent with n. Our work is in the same spirit. So when we think the sparsity k and the error epsilon are constants, our goal is to achieve constant sample testability. So that's all I want to say about property testing. The second strand of research I want to mention here is some linear algorithms in learning. For example, Cohn and Valiant considers how to estimate the variance of the noise and the L2 norm of W when the algorithm receives random samples of the same form like ours, that is x, w dot x, plus an independent noise eta. Note that there is no sparsity assumption in this work by Cohn and Valiant, so the recovery of W takes n samples. Somewhat surprisingly, they show that root n samples are enough to estimate these two quantities. So in some sense, our problem can also be reformulated as what partial information of W can be learned more efficiently. The rest of the talk that's all I want to say about the previous results. The rest of the talk is organized this way. I will go over the formal statement in the next slide, then discuss some high-level ideas. So due to the time constraint, I will only state our main theorem for estimating the distance between W and k sparse vectors. So let me go over this theorem. Let W be an unknown vector of dimension n such that its L2 norm is a constant, say between 1/10 and 10. So let D be the distribution to generate the coefficient vector x. Our algorithm requires D to be ID product, say D naught to the n. So in the previous special case of plus minus 1 vectors, D is the uniform distribution over plus minus 1 to the n, and the D naught is the unbiased random variable plus 1 or minus 1. So this is the generalization we mentioned earlier. So our algorithm further requires D naught, the distribution generating every entry in X, to be non-Gaussian. Okay. So then, given any distribution generating the noise eta and its sparsity k and the error epsilon, our algorithm receiving samples of the form x w x plus eta, where x is generating from the ID product distribution, has the following guarantees. It will compute the minimum distance between W and all k-sparse vectors V up to additive error epsilon. Okay. The sample complexity of our algorithm is a constant independent with M, but it depends on the entry-wise distribution D naught, the error epsilon, the sparsity k, and the distribution generating noise eta. Okay. So one caveat about the running time of our algorithm is that it will be a constant if my algorithm can skip the reading of x in every sample, but just read the label w.x plus eta. So this is saying our algorithm will only use the information in the label to estimate the distance. A few more remarks. So first of all, this algorithm clearly satisfies whether W is k-sparse or far away from k-sparse, because we compute the distance between W and k-sparse vectors. The second thing is that there are three conditions to make our algorithm work. So the distribution D generating X has to be ID product. D naught, the entry-wise distribution of D, has to be non-Gaussian. And our algorithm has to know the distribution generating the noise. So these three conditions are shown in the red color. But I want to say that we will give three lower bounds to justify these conditions. Basically, we show that weakening any of the conditions will make the sample complexity grows as omega log. So when D is a Gaussian distribution, or when D is not ID product, like the mix of two-person distribution, or when the distribution of the noise is unknown, the sample complexity will depend on it. Okay. So that's all I want to say about the lower bounds. Finally, let us discuss upper bounds. So you may ask, can we get a uniform upper bound on the sample complexity? This turns to be too much to expect. It will depend on how far is the entry-wise distribution D naught from Gaussian. But for nice distributions, like the uniform minus 1, 1 to the n, we have an explicit bound k over epsilon to the order of k. So that's all I want to say about the theorem. The rest of the talk, we will discuss our technique. So maybe the most intriguing question from the theorem statement is where does the requirement D is not a Gaussian come from, or why our algorithm works for any non-Gaussian. To answer these questions, let me introduce cumulants. So cumulants are alternatives to the moments of real random variables. So these are the first three cumulants in terms of the moments. The first cumulant is still the expectation, the second cumulant is the variance, and the third cumulant becomes more complicated. So in general, there is an explicit formula to express the case cumulant in terms of the first k moments, and vice versa. The formal definition of cumulants will go through the cumulant generating function, which is defined to be the log of the moment generating function, that is, expectation of e to the zeta x for variable zeta. So what I want to say here is that the cumulants will inherit lots of properties from moments, but one unique property that will be extensively used in this talk is linearity. So when we have two independent random variables, x and y, the jth cumulant of x plus y is the summation of the cumulants of x and y separately. Compared to moments where linearity is only true up to order 2, this is true for any order of cumulants. And the second property we will use in this talk is homogeneity. When we rescale a random variable x by a factor c, the jth cumulant will be rescaled by a factor c to the j. Okay. So that's all I want to say about cumulants. Now I'm ready to tell you the basic idea. So as mentioned earlier, our algorithm will only read the label in every sample. So we consider the random variable corresponding to the label, that is y equals w.x plus eta, where x is generating from the ID product distribution denoted to the n, and eta comes from an independent distribution. The main observation is that for any j, the jth power of the Lj norm of w is equal to the jth cumulant of y minus the jth cumulant of eta, normalizing by the jth cumulant of d naught, where the jth power of the Lj norm is defined to be the summation of wi to the j. Okay, the proof is simple. So note that y is nothing but a summation of n plus 1 independent random variables. So using linearity, we know the jth cumulant of y is the summation of the cumulants separately. Then we use homogeneity to pull out the coefficient wi to the j. And because every entry in x is sampled from d naught, so we get kappa j d naught. After normalizing, we get the red equation. Okay. So this red equation will be the key for us to design the distance estimation algorithm, because it brings a way to estimate the Lj norm of W. So if we take a closer look on this equation, because the distributions of d naught and eta are given to the algorithm, we can calculate the jth cumulants. So at the same time, we have random samples of y to estimate its first k moments and the jth cumulant. Okay. So as long as the denominator kappa j d naught is far away from 0, we can estimate the Lj norm of W with constant number of samples. The Lj norm of W will shed lots of information about W. For example, the limitation of the Lj norm is the L infinity norm, which is equal to the absolute value of the largest entry in W. So based on this limitation, we design an algorithm to estimate the largest k entries. So basically, we choose k indices j1 till jk property and estimate the Lj1 norm of W till Ljk norm of W. So the estimation of the largest k entries are enough to test whether W is k sparse or far away from k sparse. So I do not have time to go over the algorithm, but I want to discuss this condition that the jth cumulant of d naught is far away from 0 in the next few slides. So first of all, I want to address that this is a very non-trivial condition for cumulants. So unlike moments, cumulants of even order can be 0 or negative. So the fourth cumulant is the fourth moment minus 3 times the square of the second moment. The main thing we want to figure out for cumulants is how many non-zero cumulants does d naught have. So this is simply because our algorithm needs at least k non-zero cumulants to estimate those Lj nodes. So one bad example is Gaussian random variables. From the cumulant generating function, all cumulants of order higher than 2 are 0 for Gaussian distributions. So this answers the first question, why our algorithm excludes Gaussian. But how about the order distributions? So happily, this is the only case that can go wrong. We have this deep result from probability theory by Martin-Kawicki, saying if D0 is a random variable with a finite number of non-zero cumulants, then D0 must be Gaussian. So equivalently, this is saying for any non-Gaussian D0, it has an infinity sequence of non-zero cumulants. And we can pick those k indices in this sequence to estimate those Lj nodes. Okay, this intuitively explains why our algorithm works for any non-Gaussian. But we need more to obtain explicit upper bounds on the sample complexity. So we want to bound these k indices J1 to Jk. At the same time, because the J's equivalent of D0 is in the denominator, we want to null bound it. Okay, so the final thing I want to say is that we give a constructive version of Martin-Kawicki's theorem to finish the whole proof. Let me go over this theorem. Let D0 be a real random variable with variance 1 and support from -b to b. So b is a way to measure how far is D0 from Gaussian distributions. So then given any threshold t, if you ask me where is the next large non-zero cumulant, so we can find one that is the most exponential large in t with base b, such that the j's cumulant of D0 is at least double exponential small in t. Okay, so this finishes the whole theorem. A few remarks. So first of all, to the best of our knowledge, this is the first constructive upper bound in the context of Martin-Kawicki theorem. The second, the final upper bound on the sample complexity becomes a tower of exponential type. But for nice distributions like the unbiased coin -1, 1, we can choose these indices just to be the first k even numbers. Okay, so that's all I want to say about our algorithms and techniques. So let me wrap up everything. So our algorithm decides if W is k-sparse or far away from k-sparse given samples where X is generating from IID product distribution, and the label is W dot X plus eta for known distribution of eta. The sample complexity is a constant independent of its own. And our algorithm is very robust. It estimates the largest k entries in W and finds the distance of W to the closest k-sparse vectors. So that's all I want to say today. Thank you very much.